Thank you. So usually I just immediately click on from the very first slide, but several people have actually mentioned just how many partners are in this consortium. They're all Irish companies, Irish government organisations and agencies, and universities and research institutes as well. But actually, the fact that there are so many partners is actually something that's relevant to this presentation. So my name is Cathal. I'm from University College Dublin in Ireland, and I'm part of the School of Mechanical and Materials Engineering there. And at the moment I'm working on this project, the ECIP project. A little bit about myself. It was great to actually come to this conference and to hear that people are looking at computer science and maybe some of the lessons that can be taken from computer science and brought to construction. And I said, I must be in the right place because I'm a computer scientist. I actually know very little about construction. So if someone starts asking me about U-values or densities of walls or things like that, I'll just refer you to my colleagues here in the back of the room because I know very little about that. For many years I worked in industry, and again, as a computer scientist, it's kind of cool because you get to work in many different domains. So I worked first in telecommunications, then in AI-related projects. And I found my way to UCD then to work on several large consortia, essentially as a software engineer, but increasingly as a researcher as well. And I guess it was a little bit of that experience from industry, as well as the experience of working with such large consortia, and I suppose the experience of what happens, some lovely elegant software solution that works perfectly well in the lab, and then you bring it to the real world, and it starts experiencing, I suppose, what we call friction. We'd like to talk a little bit about that and essentially how our solution evolved to use some of these W3 standards to help us overcome those problems. So we'll talk a little bit about the issues that we encountered. So I suppose first the problem that we were trying to solve in both projects, the issues that we encountered, and then I think our efforts to overcome those issues. So essentially achieve the goals of the project, but overcome, I suppose, these frictions that we encounter when we go to the real world. So the core element that this project is trying to solve, or our part of this project is trying to solve, is actually quite similar to the previous project. We want to support the development of decision support systems that operate at a district scale. And basically where we've got many different types of information input, many different types of formats. So for instance, we've got city GML, we've got IFC files, but then we also have some custom information that could come in the form of an Excel spreadsheet from one consortium member. We might have to access a programmatic API, a programming interface, to access the other information. It might arrive to us in JSON or XML. So we have to deal with many different types of formats and essentially then unify that information so that other software systems can access the information, use it to run simulations. So it's a pretty standard problem. Initially, we had what we thought was a very elegant solution, and then people said, but can we change one little thing about this? And can we change one little thing about that? And that's essentially then where our software, basically where we decided to move towards a standards-based software solution and make our solution a little bit more flexible, make sure that it was decoupled so that the different software systems weren't dependent on each other. And because it's a government-funded project, and because there's government agencies involved, ideally be as cheap as possible to use, both in terms of hardware, in terms of training personnel, and also in terms of implementation and maintenance. So the data exchange problem has been around for a long time. As long as there's been information, people have been swapping information. And as long as there has been information, people have been trying to merge different sources of information. And essentially, the data exchange problem has three facets to it. So one is the heterogeneous nature of information. How do we know if we have information in format A and information in format B, that two pieces of information in both of those formats are talking about the same entity in the real world. So basically, how do we unify the information? Then you've got a temporal aspect to the data exchange problem. How do we know that these pieces of information are harmonized across time? How do we know that there hasn't been a change, that some piece of information that we're including isn't out of date, whereas all of the others may be up to date? And obviously then that would cause erroneous results. And then there's the systems level of the exchange problem. Simply, how do we access the information in the first place? How do we present it in a form that we can pass to other software systems? How can we make these systems work together so that they can form tool chains? And ideally, how can we support some degree of automation in that tool chain process? So this was, I suppose, the original view that we had on data exchange. And then we went from I'm sure people here are familiar with the concept of a software readiness level or a technology readiness level, a TRL level. So oftentimes you talk about a TRL level of 3 if it's a kind of a lab system, lab-based that works in the lab, but then you move to TRL 6 and 7 when it goes and is used by other people to solve real-world problems. And immediately once you start making that change, in TRL level, you start to encounter, I guess, what I was calling these frictions. So obviously issues of cost. The hardware that will be used, who's going to pay for that? Where will it be hosted? Who's going to maintain that hardware? If something breaks, who's going to pay for that? Then we've got the soft skills. So this is actually a poster that we have in where I work. So it's kind of the human with the computer for a brain, which I think some of my computer science colleagues may think is how it works. But those human costs of the software engineer and I suppose the training that's required to use particular software systems. Then once you're collaborating with groups, some of those may be commercial. They'll have commercial sensitivities about their information. They may not want to share the information with you in the first place. They may want to control the information, or if they do, they may place restrictions on where that information can be hosted and other factors like this. And finally, then you've got the regulatory aspects. So again, GDPR. Once you're dealing with real-world problems, you're dealing with real people, and obviously you must be compliant with regulations around data privacy and so forth. The second, I suppose, aspect that we encountered in the real world, and I think this was one that I can speak about from personal experience, was basically the effect that your software organization or the software architecture, what are the implications of the software architecture? So sometimes something that seems quite expedient when you're at design phase, when you actually come to bringing something to a real project, then it can start highlighting some issues. So for instance, if your software is quite tightly bound, if the systems are dependent on each other, then if you make a change in one part of the system, it can have an impact on other parts of the system. So that's not an ideal circumstance, and it's especially so in the case of large collaborative aspects, because sometimes those changes will have knock-on effects and it creates resistance to change. Some people are very keen for the change, others are not so much keen for the change. But one thing is that for sure, whoever is in charge of the data management, if the system is tightly bound, they end up doing the majority of the work in that case. So this was something that we experienced, I suppose, in one of the projects, and then we wanted to move towards a much more fluid and much more flexible software architecture where we could push some of the responsibility for updates and maintenance back to our collaborating partners. So in order to achieve this, we created a server, and rather than acting as a data store, the architecture that we tried to achieve was to act more as a data registry, so that information could be discovered through our server, information could be accessed through our server, access control could be managed through our server, but that the individual information providers would be the ones that were responsible for actually serving the information. So to do this, we used W3 consortium protocol from linked data called DCAT. So we used that as a registry so that information could be located. And we developed an ontology that provided a common context for that information. So basically, we place information sets in both space and time. So we try to give them a place, and we set that information in a particular time period as well. And then I suppose the important part, we try to make sure that our collaborators use that schema and use that as a reference point for the information that they provide. So our ontology, just on the left, again, it's my left and right. It's probably another point. I'm always confusing the two. It's another good reason for me not to be in construction, because everything would be reversed. Essentially, the type of query that we'd like to be able to support would be something like this. What were the humidity readings in all zones, in all buildings equipped with a particular type of sensor when the external humidity was at a particular level? So that's a query that spans district information and also includes then information that will be aggregated from the building level. So there might be some sensor information that's been captured and stored at the building level. So in both of those projects, the essential organization was that the district geometry was expressed in CityGML, and the building geometry and other information about the building was captured in IFC. And then third-party, generally custom information sources were provided to augment that core information. So we developed a schema then, an ontology that would allow us to unify those different formats so that we could then formulate our queries across those formats. So I have a pointer. So if we just see here, we have an entity, so that would represent some construct in the district. So generally, it could be a site, then a site contains a building, and then buildings contain stories and zones and spaces and so forth. And every entity can be contained by another entity, so it creates a vertical hierarchy where you're able to drill through detail. And also then entities can contain other entities, so that continues that kind of vertical motif. But equally then an entity can be equivalent to another entity. So this entity that we have in IFC can be equivalent to some other entity, in our case in CityGML. And all of those entities then have IDs and a particular format and the URI that's associated with the entity to identify the information source that's associated with it. We cheated a little bit. The server, when it's deployed on the cloud. So basically, we've created an image that can be deployed to AWS or Azure. So Amazon provides cloud computing. We've developed this as an image that can be deployed. Once you create an instance of the server using one of those services, you can then browse to the server and initialize the project using a wizard-based, a web page-based admin interface. So you can add users, give those users responsibilities within the project and so forth. Also then you can upload your, again in our case, a CityGML file, and then have a visualization of that file, and through that you can associate IFC. So that's actually how we populate. It's through that admin action. That's how we populate the information that's associated with the ontology. So just to, I suppose, very briefly, because I've got just about a minute, very quick look at the architecture. So on the side here, so essentially all of this is that cloud instance of a cloud instance computer. So our CityGML or urban model is residing in a post-GIS database. In our case, again, in our two projects where we're using OpenBIM server to manage our IFC. And then we created two custom interfaces to those. Well, just queried the database using this one. And this one, then we used the low-level interface and connected programmatically to the BIM server. And then that information, along with the input from the setup wizard, is used to populate that contextual core to the project. Then we have Apache Jenna is supporting our server, and we use that then to implement DCAT. Information from an admin perspective can be passed to the server through the JSON interface. And also then the server can accept SparkQL queries, which are federated then. They can first be used to query what information sources are available so that people who are constructing queries who want to access the information, they can realize what information sources are available and then generate SparkQL federated queries that query the endpoints that others have exposed that are part of our server structure. And then finally, it's kind of outside of the scope of the talk, but we have a very simple notification service as well that allows us to create events to say that one particular process is completed that generates notifications for that others can subscribe to. But I think that will be the source of a whole other talk. So that's about it.